Hi, I'm so happy to be here. Thanks for having me in Velocity. Today we are going to talk about distributed tracing. But before we start, let me introduce myself. I am José Carlos Chávez. I work at Typeform. Typeform is a conversational data collection company. And we provide a platform so our users can create forms that feel more like conversation. That's why we have a higher completion rate. And I am also part of the Zipkin core team. Zipkin is an open source distributed tracing tool that I will talk about later. And I'm also a contributor of some other observability projects. So let's start with distributed systems. Well, a distributed system is a collection of independent components that, from user perspective, appears to be a single coherent system, right? It has three main characteristics. The first one is concurrency. So concurrency is about dealing with many things at once, right? And the second characteristic is that there is no global clock. That means that every single service that is running in its own host has its own notion of time, right? Because it is distributed. And the third one, and the most important one probably, is that they have independent failures. And failures can have three types. The first one is faults in the network. Because, yeah, if you read the Building Microservices book from Sam Newman, he establishes that network will fail, or can fail and will fail. And it can be because you have a DNS problem or whatever that doesn't allow your components to connect to the internet. Then another point of failure could be the host, the actual computers. Let's say you run out of disk, or there is an error in your disk, and your host is not able to operate anymore, right? And the third one is independent component failed, because your components can fail, right? You can have an unhandled exception, a fatal error that makes your component to not to be operative anymore. What is important about this last point is that you can see that there are many ways your system can fail, so you better design it to fail safely, right? But before we continue, I want to ask you to take a couple of seconds to think about a distributed system you are familiar with, something that you see day to day, right? I want to introduce a distributed system that should be familiar to all of us, so we are all on the same page. This is a pretty simple distributed system. As you can see, from the person perspective, it's a set of independent components that act as a single coherent system. And this system has just one use case, which is I open the tap and the water flows out. Pretty simple. But let's say we have a small leak here that causes a water loss. Well, what will happen is that that leak will end up in a decreasement of the pressure of the water. And then the water will take a little bit more time and flow through the pipes. But eventually, the water will flow out, and the user will be, the person will be happy. But let's say now we have something bigger. We have a clog in the pipe. Well, again, as the pipe is clogged, the pressure will decrease to zero, and even if the water managed to flow, it will be just drops. So the person will perceive this as a latency first, but then this person will wait and will realize that the water doesn't flow, right? And will get angry, of course, and will scream in Unicode. What is interesting from here is that this person can perceive that there is something wrong in the system, but might not be able to pinpoint where the problem comes from, right? Who is an expert in piping systems. And does this situation sound familiar to you? Is there any case in your day-to-day work where you perceive that there is a failure, or you suffer a failure or a latency, and you are not able to pinpoint easily where the problem comes from. Well, to me, this is a very common situation, because as software engineer, you have to deal with these kind of systems. Because modern internet services are implemented as large, complex, distributed systems nowadays, right? When your system had a couple of components, it was easy to understand the problems by looking at single components in isolation. Now, a user request traverses dozens of services, so you cannot continue understanding what the problems are by looking the components in isolation. You need to understand interactions, right? Here we have a pretty simple API. We have a media API. We have an API proxy in front, and that API proxy will request the media API, but first it will request the auth service to determine whether this individual can access to this information. Does it have the right token? And once that is done, the media API will request information from the image service, and from the image service and from the video service, and then compose it up and send it back to the user, right? Let's say now we have a small latency in the image service. Well, that latency will make the request to take a little more time to respond, and then consequently the media API will take a little more time, and again the API proxy will take a little more time, and the user will perceive that, okay, this was slow, but it worked out. An engineer looking only at the overall latency might know that there is a problem, but they might not be able to pinpoint which service is at fault, right? First of all, because we are in a distributed environment. And in such environments, we probably have independent teams, right? Teams that build their own software and operate it, and they do at their own. Not every single engineer has to know what are the services included in one specific use case, right? And even if you know what are the services involved, not every engineer is an expert on every single service, right? You can maybe when you are in a company with 10 microservices, but when you're in a company with 400, then it's impossible. But let's go further. Let's say you have now an error in the database, a TCP 2003 error, cannot connect to the server. Well, the auth service will have no other choice than replying with a 500 to the API proxy. And then that response will be forwarded to the user. And again, if you have to fix such a problem, how would you aim to fix this if you don't understand what is happening behind the coatings, right? Yeah, as you can see, this is complicated stuff. So let's go back to the pipes where things were simpler. Because in my mind, it will be awesome if an error could tell you, hey, I am here. Oh, sorry. Hey, I am here. I am clogging your pipes, right? Because then I will be able, with that information, to go fix the problem and then keep the person happy. And you may be thinking, we have something like that in software engineering, right? We have logs. Yes, and we had logs for 40 years. Problem with logs is that this kind of situation usually look like this, right? We have concurrency. Because services on machine might be shared simultaneously by different clients. So this situation will end up in this set of logs, which I kindly colored for you, but they are not in real life, believe me. Because logs represent events in the system. There is no scope, no context around logs, right? And I'm not even talking about asynchronous operations. And you might be thinking, okay, but I could add some metadata to my logs. I could add the request ID, the user ID to enrich these logs, and then I can correlate them and blah, blah, blah. And in a 3 a.m. o'clock on-call duty, you don't want to do that. You don't want to put all the pieces together and reconstruct the story because that will never happen, right? Because logs will tell you that something happened, but it won't tell you why, nor how. It won't tell you what was happening at that time, so I did this operation and I failed. That won't happen from logs. So how can my dream become true? How can my error yell at me and tell me, I am here, fix me? Well, there is when distributed tracing comes to unclog your pipes. Distributed tracing is a way to understand what happened in your request. It's about tracking and analyzing requests as they bounce around your distributed architecture as a whole. You can think of it as an action replay. In this graph, which is the most popular graph for distributed tracing tools, you can see how this happened, what happened in the request, because this is request scope. You can see one single request, the concurrency is mute now. You can focus on it. You can also see causal relationships. You can see that the API proxy requested the out service first, and then requested the media API after, and the media API subsequently requested the videos and the images, right? You can understand dependencies. It's also timeline, because you can see how all this happened across the time. You can understand latencies. In this specific case, you can see that the image service took much more time because it couldn't find the resource in the cache layer. It had to go to the origin and reproduce all the data. You can understand it, right? And you can enrich your data with annotations. You can say, OK, this error happened here. This specific operation happened in this host. You can enrich all this information. This is in contrast to traditional monitoring, which focuses on individuals, on each service, rather than in the use case, right? So let's see what answers I get from distributed tracing. Well, the first one is what services are involved in a request. I can understand what is the path now. The second one is what happened on each service in that request. How your services are connected. What is the critical path? Critical path is something very important. I will go and explain in a few slides. But it's important to know what are the most important pieces that happen in a request. What were the ones that has more impact in the user? And finally, who should I page for this error? That's important as well, right? But don't take me wrong. I am not saying distributed tracing is the silver bullet that will fix all your operational problems, because it's not. In this graph, you can see distributed tracing and friends. How distributed tracing is complementary to all the other signal collection means. This graph is made by Peter Burgon, and it describes, for example, the main characteristics of tracing metrics and logging. For logging, you have that logging is about events. It tells you that an error happened. It's focused on events. Metrics will tell you how many errors of this time happen. It helps you to understand trends, but there is no context around metrics, right? And then you have tracing that tells you what happened and the impact of that as it propagates across your services, right? But let's focus on the benefits. Because distributed tracing will provide requested scope, actionable feedback, right? It provides you a system insight because it clarifies non-trivial interactions and gives visibility to critical paths and dependency. And now I will tell you about critical paths. Because not every piece of what happened in a request is critical, right? And this is something that Google discovered when they were in the journey from splitting a monolith into microservices. And they discovered that they were dedicating time and effort to improve operations that were not affecting user latency, right? Let's say you have two concurrent requests or two parallel requests, and one is always taking double as the other. Well, it doesn't make sense to dedicate time to fix the faster one, right? Because there is the other one that you have to wait for to finish, and it will take double of the time. And you can say, OK, but why will I improve something that is already fast? Well, I told you two parallel requests, but imagine you have 100, right? You don't know. So yeah, it's important to understand what the critical path is, what are the dependencies. And one of the other benefits of distributed tracing is that request effect is not constrained to the request lifecycle. That is very helpful when you have a single operation. When you do a request and then the server responds with 202, and then things happen after, right? You want to also see that as a whole. What happened when I replied to the client and what happened after. Let's go to the trace anatomy. Well, a trace tells you the story of a transaction or workflow as it propagates through a distributed system. It shows the execution path, right? Then you have the span, which is a single unit of work that can represent things that are error-prone or that can have latency. For example, an expensive operation, an HTTP request that can fail or can have latency, a database call that is, again, expensive. You have a context that is something that should be propagated across all the components in the distributed architecture. And it can be propagated through HTTP headers or Kafka messages in the metadata or SQS metadata. Then you have tags. Tags are a way to group a span by a meaningful concept. For example, I want to group all the spans for this request ID. Or I want to group all the spans that happen in this host so I can understand what is happening, right? Or in this specific MySQL instance. Then you have logs that mark meaningful moments in your span lifecycle, right? That are timestamped. For example, I had this error here, but I will keep going, right? But the error happened at this time in the timeline. So, what are the elements of distributed tracing? Well, this is a very nice analogy developed by Nick Munroe from Nike. And as in every other three-legged stool analogy, every leg depends on the other two to work properly. We have three legs in distributed tracing, and we will explore them. The first one is inbound propagation. Well, inbound propagation is what happens when your service processes a request or consumes a message. In this specific case, we have that the API proxy is requesting the media API. And for that, the media API will create a span representing the operation and saying, this is the span I create as part of the trace with ID ABC123, right? Then we have outbound propagation. Outbound propagation is about when your service makes an outbound call to another service. For example, when the media API requests to the video service. For that, the media API will inject the context into the HTTP headers, and then the video service will receive that context and create, again, a server span saying, I am creating the server span as part of this trace because of the HTTP call the media API made to me, and with the trace with ID ABC123, right? Basically, everyone is reporting their part of the part of their story, right? And finally, we have in-process propagation. In-process propagation is about performing an operation inside your component, doing a Redis get or doing a SQL call. Again, when your component does this Redis call, it will create a span saying, I am doing this Redis call with this information. It took this time, and I am doing it as part of the trace with ID ABC123. As you can see, each part needs the other to propagate the context in order that all can be grouped in this way, right? After all of the pieces reported their part of the story, the distributed tracing tool will summarize the map and put it in this way, which is some sort of a tree graphic with parent-child relationships, right? Timeline. And you might be thinking, yeah, this is too good to be real, right? Is there any downside? Yeah, there is. There is overhead, because nothing is for free in life. We have two sources of overhead. We have overhead for users. Observability tools are meant to be unintrusive. They are meant to not to affect the normal workflow of your service. That means that, let's say, you have your code with instrumentation ready to report to your distributed tracing server, and let's say that code had an error. Well, that error should never be propagated up to the user, because it's not supposed to affect the life cycle. It's also supposed to be optimized to add as a small performance penalty as possible, right? Otherwise, you will end up in the observer effect, where you modify the experiment by observing it, right? Then you have the sampling, which is also another attempt to reduce the overhead. Sampling is basically taking a sample of all the requests and only store that. Because it makes sense, right? For large-scale systems, you only need a small piece of it to understand what is happening, where the source of latency is and what are the errors. For small or low-traffic systems, you need more, and you can adjust yourself. Because in the end, it's an operational cost as well, right? You will be maintaining another bucket where you throw traces like you do with logs. But now these traces has more information, so you have to make your trade-offs. Sampling was described at first by Google Dapper, which is a paper published in 2010 by Google, where they were explaining all these learnings about debugging in production. And the third point is, don't trace every single operation. You don't want to trace everything. You only want to trace what is error-prone, what is interesting to you. You don't want to trace how your application sums two numbers, right? Because if that fails, then you have other problems. And you only want to trace what is interesting, what can fail, and you will observe in the future. This is for users. For developers, we have one challenge, which is that not all the libraries are ready to plug instruments on it. But the good news are that for most of the libraries, there is. If you happen to use a framework, it's very likely that there exists already instrumentation to it, so you don't have to write yourself. And if you have common frameworks, like custom frameworks, like your own HTTP client or your own server library, you can write instrumentation for it, but you can write instrumentation only for the common components. So you don't have to write that code for every single service, just for the common libraries, right? So now let's introduce a very nice distributed tracing tool, which is Apache Zipkin. Well, as I said, Apache Zipkin is a distributed tracing tool. It was based on Big Brother Bird, which was a tracing system at Twitter, and also inspired in Google Dapper. In Google Dapper was this paper published in 2010 by Google. It was open sourced by Twitter in 2012 and just joined the Apache Foundation this September. Key points of this is that it has a mature tracing model emerged from users' needs, right? Zipkin is not a vendor. It's mainly open source. And it's used by large companies like Netflix, SoundCloud, Yelp, and by not so big ones. There are small companies already using Zipkin as well, like Typhon, for example. It has a strong community. Most of the work in Zipkin is volunteering, so it gives a very nice feeling of open source. This is Zipkin architecture. As you can see, it's a fairly simple one. You have your services that are instrumented. I keep repeating the word instrumentation, instrumenting. but I didn't give a formal definition of it. Basically, instrumentation is the possibility to plug instrument and collect signals in your libraries or your system. So once you have your service instrumented, that will collect the spans internally and report it to a collector in Zipkin. Through HTTP, through Kafka, depending on your load. Then that collector will persist all that data in a storage, and then there is an API where you can query, right? And then there is a UI, of course, so you can use it. This is how Zipkin looks like. As you can see, you have a list of traces, and you have a set of filters. You can filter by service name, because you want to inspect traces in that specific service. You can filter by span name, because you want to trace, or you want to look at a specific endpoint. And you can also use the annotations query, where you can filter by request ID, filter by host, filter by error. And this is a trace overview for Zipkin. As you can see, this is a tree view of what happened in the trace. This is a tree of spans. You can see how much each one took and how is the relationship parent-child, right? And this is all across the time. So you can understand what was the timeline of what happened in your request. As I told you, you can enrich this data with logs and tags. You can add a request ID. You can add a host name because you want to separate it by instances. And this is how it looks when you have errors. You will see that they are marked in red, but more important, you will see how this error is propagated upstream from the video service to the media API and from the media API to the API proxy. And this is what I was mentioning about a sync operation. Because after the request responded with 200 or 202, let's say you have a tracking service after that that is doing some other job. That is expensive, that's why you don't want to do synchronously. You can keep that in the same trace, and then you can see the overall picture, right? So that's pretty good. And last but not least is that you have a dependency graph you can get out of your data. This helps you to understand what are the interactions between your services and how they are connected upstream, downstream. And you might be thinking that this is a ridiculous service graph, but believe me, this will help you when you have this kind of architecture. And this is it. Thank you.